First thing I would like to go through with you is the limitation of the first generation of implants. Those are the ones that we talked about previously, that we started doing some kind of solutions to bypass spinal cord injury by reading from the brain activities using surface electrodes, and then we send it to controller, and the controller then will be feeding stimulation to the muscles, and then we get a feedback from it. And that's how we are trying to bypass a spinal cord injury. And this actually was the first generation or first attempt that we did in order to use functional electrical stimulation in rehabilitation engineering. And if you recall from the last lecture, we talked that we need a controller, we need a stimulator, and then we need leads and electrodes to be able to have this system functioning and working. The limitations of this generation, first, we have something called reverse recruitment. And what we mean by that is that we have fast twitching before slow twitching fibers that could lead to muscle fatigue. And if you recall from previous lectures, we talked that when we discussed muscles, we said that we have two types of fibers, the fast twitching and the slow twitching fibers. Each muscle fiber is one cell. So reverse recruitment, that's a problem of using functional electrical stimulation in the first generation. And as I mentioned before, all these challenges are topics for research. That is ongoing research right now in a lot of laboratories in order to overcome these challenges. Behind every challenge, there is a hidden opportunity, and that's what we want us as biomedical engineers to be looking for. Another challenge is that we have lack of closed loop control via afferent pathway. And what I mean by that is that when we were sending the signal to activate the muscles, so we read that from the EEG, we have the controller, the controller will do stimulation, and then this afferent pathway is the signal that is going back, a sensory signal that goes back to the brain. But because we have the injury here in the central nervous system, we don't have that pathway. We can measure some feedback, but it's going to be very weak in order to modulate or affect the stimulation. And that was a challenge that need to be solved in the next generations. So it's okay that it's fine that we can stimulate the nerves and the muscles via the efferent pathway, but the problem is we need to have also feedback from sensory neurons in order to have the afferent pathway functioning. You need both pathways to have a smooth movement. We have also a problem that is, or a challenge is steep recruitment of muscle fibers, which result in robot-like movement. And we need to have it more smoother recruitment. Also, we have some we called inflexibility of stimulation patterns, which mean non-adaptability. So if you want to raise your hand or you walk, you'll be walking or raising your hand the same amount if you are using a functional electrical stimulation solution. Also, we have adverse reaction to electrode interface due to biocompatibility issues, and we're going to discuss this more when we talk about electrodes and how they are designed, how to use them. And also, because of biocompatibility issues, we could end up with encapsulation and the surface foiling of electrodes. Because I probably mentioned this last time in the lecture that if a material in the body it's not compatible, the body will try to dissolve it. If it's cannot be dissolved, it will be encapsulated by fibers, and this will eliminate actually the functionality of the electrode, because now it cannot measure the electrical activity. It just works as an insulation on the electrode. And then we have something called spillover, which is when you are stimulating specific muscle fibers, the activation could go to neighboring muscle, and that will go to result in recruiting muscle fibers that you don't want to recruit them. So I hope that this is an overall, or a big looking at the big picture of the challenges and the limitation of the first generation of implants. Now, I would like to talk about bionic devices to restore locomotion, and this is the second generation of devices and solutions that uses functional electrical stimulation. Remember, we are talking about functional electrical stimulation as an instrument, as a medical instrument used in healthcare and especially in rehabilitation engineering. So the first the first generation of bionic devices. And when we say bionics, we mean that we are trying to mimic the original function, the natural functionality of the organ or tissue that we're trying to replace. So we have something called epidural spinal cord stimulation. And this is a type of stimulation of the dorsal structures of the spinal cord. And if you look at this image here, the system consists actually with a controller and a battery that is going to be sending signals to parts of the spinal cord, neurons of the spinal cord. And why the reason for doing this is that it is when it combined with weight-bearing treadmill therapy, it is very effective in restoring locomotion, which is the ability to move. And it facilitates gait. It was successful in facilitating gait. And if you look at the image to the right here, it tells us where we are going to place these electrodes that will stimulate the nerves of the spinal cord. So those are the thoracic and those are the lumbar vertebrae. So vertebrae. So it's a very effective tool to facilitate gait, and it's effective only in incomplete injuries. So if you have a complete injury of the spinal cord, which means a complete cut in the spinal cord here, we cannot use this technology. It works well with partial injuries of the spinal cord, and it lacks the selectivity and muscle synergy, which means we can, because we are stimulating a bunch of nerves in the spinal cord, we cannot select which muscles we need to target or which muscle we need to stimulate. And the other thing that it lacks actually muscle synergy, which means that if you have multiple muscles or muscle group consisting of multiple muscles that work together in synergy, this cannot be done when we have epidural spinal cord stimulation. Still, it is very, it's successful in facilitating gait for people with incomplete injuries. All right, so this is the first instrument, device, or tool that we use to help restore locomotion. Then we have an improvement in such devices with the invention of the intraspinal micro stimulation, and well, it's tapping into patterned movement of the leg, so it helps improve synergy compared to the epidural spinal cord stimulation. And usually we have wires, electrodes, to stimulate something we call the ventral horn, or the nerves in the ventral horn. So the ventral horn is this part of the spinal cord here. This one here and that one here. That's called the ventral horn. And actually, you have axons of neurons that they control the lower part of the body, or the movement of the locomotion of the lower part of the body, and it is the best place to activate activate weight generating extension. So that's where we are, what we are targeting in the spinal cord using the intraspinal micro stimulation. So it's motor neurons. So all the neurons in this region here, which is the ventral horn, they affect motor movement of the lower extremities. And it's able to produce all the muscle synergies required for stepping, as opposed to the epidural, the first system I've mentioned. And also, microstimulation is laminar of the lumbosacral spinal cord. So we are targeting. So all of this is meaning is that we are targeting the lower parts of the lower part of the spinal cord that controls the movement of the lower lower extremities. stable recording over time, near normal recruitment order. Those are all advantages of having this type of system. And also the intraspinal microstimulation can generate weight-bearing stepping after a spinal cord injury. So this is really effective, and it's superior to epidural or peripheral nerve stimulation. So epidural nerve stimulation is the one that I mentioned before this slide, and peripheral nerve stimulation is actually the first generation where we measured EEG from surface electrodes, and then we stimulated, let's say, lower extremity muscles using an other surface or internal electrodes. So the intraspinal microstimulation is very effective in overcoming the challenges and the shortcomings of the previous generations. All right. Any questions so far about the two solution modalities, the epidural spinal cord stimulation and the intraspinal micro stimulation? Right. No questions? Yep. Right. So I hope that this is clear. I'm trying to explain to you the different types or different methodologies or tools that we can use in order to control and locomotion and improve locomotion for people with spinal cord injuries. Now, I wanted to get deeper into how can we bypass the spinal cord and what kind of components that we need to use in our system in order to be able to effectively improve locomotion by bypassing the spinal cord. So usually if we have an injury, a spinal cord injury, we are losing the pathway of the signal from the central nervous system to our lower and upper extremities. And that's where the spinal cord injury is. So what you need to do, you need to have supervision, which is electrodes to measure. So here we would like to measure or sense the signal from the central nervous system. Then we'd like to have a controller, and we can use microcontrollers like Arduino, Raspberry Pi, and then you will measure the signal using the sensors into the controller, and the controller needs to make a decision. After making the decision, and the decision will be made based on reference trajectories. For example, let's say if you are measuring EEG, we will have a database of different EEG signals that tell us that if this EEG signal is the one that we are receiving, it means walk, or lift your hand up, or do put your right leg in front of your left leg. So we have a lot of these trajectories and references. Our microcontroller will be comparing what it is sensing with what the trajectories should be. And if there is a match, there are ways for us to look at these matches for patterns in large data sets using something called the cross correlation. So if we can do cross correlation between a measured signal and the database, if we have a match, then you say, okay, go stimulate the right leg in order for it to lift the lower foot. And so that stimulation will generate an electrical pulse, and the electrical pulse will be will be sent to the muscle group, and then we will have contraction, and then we'll have movement. We can also have sensors here to detect the movement as sensory information that goes back to the controller. So those are the most important part of a device or a system that bypass the spinal cord injury. Now, you need to send a signal here as an electrical pulse to stimulate the muscle. And we have something called unidirectional electrical current pulse width modulation, which means that if you want to have a strong reaction, or if you would like to have a muscle contraction that is larger than the previous one, you can make the pulse width larger. So that's what we call by pulse width modulation. So the pulse width of your signal will decide how strong or weak the contraction is. So a long pulse means that multiple muscle fibers. A small pulse would mean that we are recruiting small number of fibers. And that's what are the most important or the basic part of bypassing a spinal cord system. And it's just a schematic and quick representation but it is used actually in both intraspinal microstimulation as well as epidural spinal cord stimulation. Do you have any questions about bypassing the spinal cord? What are the blocks and the components that we need to have in order to build such a system? Another advancement, which is looking at brain-controlled implants, and we're going to look at something called the cortical neural prosthetics. We'd like to implant an array of sensors or electrodes in the brain, and then we would like to develop an algorithm that's going to extract information from those electrodes or array of electrodes that's implanted in the brain, and then these algorithms will help us make decisions and control effectors like a robot or intrinsic muscle. This is actually the latest technology that we are working on as biomedical engineers, and different groups around the world are working on in order to develop, and there's a lot of applications. So here for biomedical engineers, if you are interested in electrodes, everybody is investing time and energy and money in developing arrays of microelectrodes. We're going to discuss electrodes in more details. We'll talk about the classical types of electrodes and typical types of electrodes. But now those are multi-electrode arrays, and they are small electrodes. Even we are now working with the nanoscale on developing these microelectrodes and multi-electrode arrays. If you are also into programming and coding and artificial intelligence, there is a lot of opportunities into developing extraction algorithms. So if you're interested in graduate school, extraction algorithms are now becoming a very, very popular topic in research. And if you like to work in instrumentation, working with effectors, designing robotics, and artificial muscles is another topic that people are investing time and money. So what we are targeting here, we are targeting the primary motor cortex, which is the blue part in this image of the brain, and its movement-related information encoded as firing rate. When we measure the action potential or the electrical activity of the primary motor cortex in this part of the brain, we are trying to collect information about the firing rate. So the higher the firing rate, it means that we have a lot of recruitment and we need to do something. The lower the firing rate, it means that we are not recruiting much muscles and we don't want to do the movement. Firing rate is directionally tuned, which means up or down. And then the extraction algorithms will come in and convert the firing rate into movement displacement by controlling effectors. The extraction algorithms will compare the data with databases available, and then we can control robots, the exoskeleton suit that is going to be controlled through the controllers relying on the extraction algorithms. And an example of this that was successful control of a robotic arm using a monkey's brain. An array of electrodes was implanted in the brain. As the monkey moves, the robot arm also moves similar to how the hand of the monkey is moving. So we proved that this is functional, and it has a lot of potential. It's still in trials, but it's a promising technology. Do you have any questions, any comments about what we covered so far? So the problems with these so far is adaptability does not extend to activating afferent pathway. So this is the sensory pathway going back from the muscles to the brain. So we need to have two pathways to have a smooth locomotion in muscles, and that is called muscle synergies. So you need to have different muscle groups acting at the same time to do a complex movement. We don't have adaptation to neural recognition, reorganization, and hyperexcitability in spinal cord injury. Also, electrodes lead to scarring if you have them for a long period of time, if they're not very, not biocompatible, and leads encapsulation and signal attenuation. So remember, if you have an electrode, it's a metal, it's inside the body, it's not biocompatible, the body tried to dissolve it, it's not going to be dissolved, it will be encapsulated, and if it's encapsulated, the electrode cannot detect electrical activity. So we have signal attenuation. And then we have inefficient power sources. You need, batteries, and you need to charge them. If you're having a device that needs power in the body for a long period of time, that's going to be a challenge. And then we have inadequate signal processing algorithms. And that's why we are investing time as biomedical engineers to learn how to use MATLAB, Simulink, and LabVIEW, all these softwares. We would like to get more and more experience in developing, codes and extraction algorithms. It's simple, but it needs a lot of practice. When we study medical signal and image processing, we will talk about, convolution and autocorrelation and cross-correlation, and how can, let's say, if you have a CT scan image and you know that how would a tumor will look like, you would like to go through thousands of images searching for that tumor. There are ways to do this, and that's signal processing algorithm. For our applications in the when we talk about functional electrical stimulation, we have huge databases of EEG signal, let's say, and we would like to look for small patterns to detect movement over the lower extremities or upper extremities. So there's a lot of potential to do this. And then we have lack of concise biomechanical models to correlate neural discharge rate, firing rate to movement dynamics and kinematics. And that's another big field and area of research that is available for if you look forward to it. So all of these are current technology limitations. We talked about 4 models or modalities of functional electrical stimulation. All of this promising challenges for us to engage in and learn more if you are interested in this field. Now, the future or part of it, we are looking for idea of shared control. Some electrodes or array, micro electrode array in the brain will be controlling something. It's a unique idea, but it's actually getting attraction. Also, we're looking at stimulating central pattern generators for rhythmic movement, bidirectional interfacing. That is to help afferent pathway and the afferent pathway synchronization. We are developing novel bioelectrodes. Ions actually are the molecules that generate electricity in the body. We are trying to generate electrodes made from polymers, from plastics, mimicking electrical conduction by allowing ions to move in and out. So we're trying to create electrodes from polymers, not from metals. And the way that they are conducting electricity is by allowing ions to move in and out, not electrons. And so there's a lot of research going on about this right now. The other thing is that we have building implantable neuromuscular implant based on work on artificial muscle. So we're trying to create artificial muscles that can contract actually to replace the tissue or our muscles. They could experience atrophy because of lack of stimulation and use, and we're trying to build that thing. And then that led us to something called body-powered implants. So the challenge of having reliable power supplies. So we're trying to use the body to power the implants, especially vibrations to charge batteries inside the body. And there are a lot of ways to do this, but I'm not going to go into it, but this is part of the future that we're hoping that we can develop. We have distributed or shared control solutions and applications, and there are a lot of startup companies that actually hire biomedical engineers that work in this field. So what we are trying to do is something called device-device communication. What do you mean by that? It means that we don't need to have implants in the brain. You will have a device that is controlling robots and exoskeleton suit. You probably have an implant in the body, and that sends a signal to a controller outside, and that microcontroller will make decisions. But rather than moving our muscles or stimulating our muscles, it stimulates a device like a skeleton suit. And that is what we call device-to-device communication. Implant in motor cortex communication with device in limb. You need only just the microarrays implanted in the body to measure the activity of the motor cortex, and then it sends the signal wirelessly outside to a device. That device is going to control an exoskeleton suit. So you don't have to do anything that is invasive with the body. Possibility of more natural movement, sensorial feedback, but not feasible for movement of lower extremities at this moment. But there are a lot of advancements happening in this field. This is the 5th system of functional electrical stimulation that we covered. I will say that we have 5 modalities, 5 different structures of functional electrical stimulation that we can use. In biomimicry, biomimetics, we are trying to develop devices that can, or solutions, or a tissue that can mimic actually the natural tissue or the natural system that we'd like to replace. Biomimetics is actually biology, mechanical, and electrical system consisting of a biological component a mechanical component, and the electrical component we call biomimetics. And we are using biomimetics into neural interfacing. What we mean by neural interfacing is that I would like to get a device or a sensor that is interfacing with neurons and communicating the signal from the neuron, the electrical signal from the neurons. By definition, biomimicry is the design of structures and mechanics closely resembling living tissue and systems. We have something called conducting polymers. You look at the neuron is capable of conducting electrical signal, but it is like a polymer. It's like plastic. It's flexible. It's not solid. It's not metal. If that is what we would like to create, artificial neuron, we would like it to resemble the natural neuron. So we'd like to design or develop something called conducting polymers. And those they have electronic conduction, ion transport. So it's not electrons. So it's ion. It's all about ions. And it has cellular adhesion and also growth. So if I really want to create an artificial neuron, so that's something we think a lot about in research. So we generated something called polyelectrolyte gel. It has mechanical and chemical properties similar to living tissue. It's biomimetic ion exchange, so it allows for ions to move in and out, which means that it's electrical activity and transport phenomena similar for the ions to go in and out. And it's also designed as a standalone electrode. So it does not need to be connected to a battery to do amplification of the current or the voltage. So all of these actually what we call bioelectrodes. So those are the basics or the dreams and desires that we would like to have if we would like to create something called an artificial neuron. Why this is important for us and what are the challenges of creating something that led us to create something like this. If you would like to measure, the electrical activity of the brain, the motor cortex, you need to have a microchip implanted in the body. And what we mean by that is that I would like to have some wires implanted into the cortex, that these wires, fine wires, very fine wires, to touch the neurons of the motor cortex. The problem was and still is, when we have metallic microelectrodes into the brain, that the interface remains the weakest link in the neuroprosthetic devices. So see all these devices, all these solutions and functional electrical stimulation systems, they are all working good, but the problem with all of them is always how we are going to get these fine wires, electric wires, to touch the neurons. So that interface is still a big challenge, and if a small movement is going to affect our readings. So that is one of the biggest challenges why we would like to create polymer-like electrode rather than a metal electrode that we're only using. Current bioelectrodes have poor anchoring at the nerve interface. That's a big challenge. We would like to develop an electrode that can have attachment and adhesion to the nerve without damaging it. And if you recall, I've told you probably in the previous lecture that if anything touches a neuron, it immediately goes to controlled apoptosis or damage. And that is a big problem for us. So we would like to generate an electrode that has some adhesive properties without damaging the neurons. So that's one thing. The other thing is the mechanical mismatch between metal electrodes and soft tissue. This mismatch has a lot of problems. That's why we would like to look at polymers so that we have similarities. Let me tell you one thing in bone. If you have, let's say, a total hip or joint, let's say a total hip replacement. So you have the stem and into the bone. So let's say here we have bone. You can see that you have a metallic part, the stem, and then you have the bone around it, and they have different mechanical properties. Because of the metal being strong, we have something called stress shielding, which means that the bone around the metal will not be sensing loads as usual because the metal is holding the largest amount of load. And that's why, and then because our body is efficient, if you are not using the calcium there, it will be dissolved to be used somewhere else. And because of that, because of stress shielding, we are seeing a lot of failure in implants because the bone around the implants is dissolving. And that is one of the results of mismatch between a metallic implant and the soft tissue around it. For example, even a hard tissue like bone, they have, they're still close in the strength, but they have mismatch, and that leads a lot of problem. Let go now. How would that affect soft tissue and that is in touch with metallic components? Also, inefficient charge transfer and signal attenuation because of the metal resistance. Remember, if you have ions inside the body, propagation of electrical signal inside the body is very fast because it is ion, and we have less resistance and we have these channels. But if you have a metallic wire, you have resistance, and that could lead to signal attenuation. And then you have inflammatory response because of the fibroblast and stimulation site. Even if you have a metal that is compatible, because of stimulation, we are noticing that the stimulation site have a lot of fibroblasts in that location. All of these challenges led us to the thinking about what can we do in order to develop better electrodes. That's the whole story, why we're doing this. If we have better electrodes, it means that we are going to develop better functional electrical stimulation systems. This way, we're going to be helping a lot of people with a spinal cord injury or neurological conditions or disorders. Now, the current solutions, we have something called surface modification of electrodes. So we have electrodes and you put coating on them so that they're compatible. And we have also conducting polymers, allowing ions to move in and out. We have something called bioadhesive molecules. So you can have a polymer that can connect, attach to a nerve. If we were successful in creating materials that can adhere to a nerve, so the result of doing such interventions like these, we have decreased resistance, which means that we can conduct electricity faster, decreased inflammation response, so we don't have biocompatibility issues, and you don't have encapsulation or foreign body reaction. We have incremental improvement, but still fundamental problems persist. Now, a novel solution, we have a paradigm shift. We are trying to do a biomimetics approach through field responsive polymers. And that is where everybody now is spending a lot of money and time and effort in biomedical engineering to create polymers that they mimic the function of a neuron. So I hope that this slide, it has a lot of information, but I wanted to explain them slowly for all of us in order to understand what is it that people are doing in biomedical engineering that might be novel and changing for people with spinal cord injuries. We have something called smart cuff electrodes. Remember that we would like to have a polymer that possess ion exchange capabilities and have some adhesive criteria. And one of these things, especially adhesion, so which means that you have a polymer that can attach to a neuron. So one of these things is called the smart cuff electrode. Poor anchoring at the interface, and we have developed something called soft thermomorphing armature. So that's anchoring. Then mechanical mismatch attenuation charge transfer. We have developed something called neuromimic electrodes for inflammatory responses, build up of fibroblasts, that's biocompatibility. We have something called drug-eluting electrodes. And all of these electrodes or materials, some of them are still experimental, animal experiments. I would like to go into the details of each one of them quickly. So let me go quickly about them. The soft thermomorphing armature, remember, it is designed to help anchoring through electrode around a neuron. So it's a polyisopropyl acrylamide. That's the material. It's biocompatible. Reverse solubility at body temperature, which means that it solidifies at body temperature. So here, what we mean by that, it's not going to dissolve at body temperature, but it will solidify at body temperature, and that's what we want. We want it inside the body to be solid and to take shape and form. And widely used in medicine for cell adhesion drug delivery, and can be fabricated as solid hydrogels. So this is the PNI-PAM. And that is a very important material in medicine. And it is what we call soft thermomorphing armature. So it's a polymer, it's soft, thermomorphing, which means that when it gets into it is like a gel or a liquid, put it inside the body and it becomes solid, and it can go around a material. So what we have is that you have two layers like this from this material. One layer is a thermosensitive layer, and then you have passive polyacrylamide layer. So that's the design. You can look at the front view and you can look at the side view. And the principle is that at specific temperature, it is flat. And once if the temperature is changing, it's becoming 37 degrees Celsius, at body temperature, it folds around, let's say, a neuron or a nerve. And that's how it is designed. So it's temperature sensitive, and the material, was patent, and there's a lot of applications for it, and it's been investigated in research. Now, the second problem was mechanical mismatch and attenuated charge transfer. So we developed neuromimetic electrodes, in which it's like the nerve. What the nerve is doing is that you have sodium current, right? Sodium going in and out. The neuromimetic electrodes have pyrrole and polysodium acrylate and deposit on metal electrodes. So we can have those to enhance, the material on the surface. And we have something called polymerization, and then deposited on. So you have even or more gels or more polymers deposited on other polymers. So in order to be able to create neuromimetic electrodes. Remember that the problem was the attenuation and charge transfer. Because of coating the material with other polymers and other materials, the conductivity is better, and the texture as well was much better. This is the value of the conductivity resulted. So higher conductivities, inferior to results obtained in the literature. Resistance greater than the platinum electrode, so decrease in impedance with coating. We have mixed results, but you can control it, and that's the important thing. So by controlling the porosity, the thickness, and the layer, the thickness of the layer, what's composed of, you can control the conductivity of these polymers. So there's a lot of work happening there. I don't want you to get into details for the neuromimetic electrodes, but the fact that we would like to create electrodes, they have better mechanical matching with the neurons, as well as to reduce the attenuation when we transfer the charges. And I think the last thing is the drug-eluting electrodes. Those electrodes are made in order to improve biocompatibility of the electrodes. Remember that with problem with electrodes, they're metal. If it's not compatible, the body will try to encapsulate it and create fibers around it as a foreign body reaction. And still, even if it's compatible, the fact that it is stimulating and have different changes in charge and discharging of the electrical activity or voltage, fibroblast will try to build there and to stop conduction. So what we have drug electrode stents. Eluting stent is that it is releasing a material that is stopping the immune system or the buildup of the foreign body reaction. You have polymers, and then you have drug-free polymers, and you have the stent. So these are important ways to create electrodes, secrete materials when they dissolve, or just to secrete materials, they don't have to dissolve, that will enhance biocompatibility and prevent foreign body reaction. The reason why we have foreign body reaction is because of inflammation. If you have anti-inflammation drugs, you will limit or reduce the functionality of the immune system in order to which creates a foreign body reaction and then makes the interface useless, because you are encapsulating the electrode, and then it cannot detect electrical activity. So you have negatively charged molecules exist as salts, can serve as counterient to polypyrrole, electrically released on activation, benzoic acid. So the whole thing is that you would like to have anti-inflammation drug that is released from your electrode with time, and that is how you're preventing the immune response from creating a foreign body reaction. So all of these technologies and advancement and ideas are now being tested, and there's a huge amount of research that's taking place just in order to solve these problems that allow us to benefit the most from the functional electrical stimulation, which is poor anchoring at interface. Remember, we'd like to anchor to neurons, mechanical mismatch, attenuation of transfer, and the inflammation response and the buildup of the foreign body reaction. So I hope that this concludes the functional electrical stimulation, and we have a clear appreciation of what functional electrical stimulation and what are the challenges and the advancement in functional electrical stimulation, because this is important when we talk about instrumentation and how to design best instrument for us. I hope it was informative and that let you think about what things you need to do and what things you would like to explore in the future.